time, let's continue the discussion we had last time. Still the fundamental equations and their relationship. Okay, so we can continue. So the main task today, we're going to do some practice to learn how this stuff works. Okay. So at the end of last class, we mentioned about the Maxwell relationship, right? The Maxwell relationship. Okay. So basically, we make use of the continuity of the equation and of any kind of the function in the 2D dimensions. Okay, if we exchange the order of the derivative, actually we got the same result. That means partial x, partial y equals partial x. Okay, so by using that kind of relationship, we got the Maxwell relationship. Okay, so can anybody recall what the relationship looks like? I put it here. Okay. So the Maxwell, we're going to use it through the class. Yeah, anybody can tell me what it looks like? I don't know how it's on the page here, unfortunately. So this is what happen if you want to use this relationship in the future. How do you get it?
Just the STPV.
Yeah, STPV, and or you can just derive it from the definition of the functions. Okay. But anyway, so I don't want to do that job myself. Can you give me a room? No, I just copy it. Okay, so what do we have is negative partial p, partial s. Oh, really? Okay. V. That's right. So this is a Maxwell relationship we use. Okay. So what's the use of it? So okay, we have this one beautiful result from the mathematical result. Okay, what's the use of it? Okay. So first of all, let me give an example. Okay? Example 1. Okay. So remember, we calculate the entropy of the ideal gas. Okay. We calculate. I think the building manager really hates us to use whiteboard. That's the reason he has higher eraser. Do you remember how did we calculate last time? I think I gave you the first question in next homework is about calculating, all right? So through the classic thermodynamics, we can calculate the entropy of the ideal gas by using the first law of thermodynamics. That's the du equals to dds minus pdv, right? This is the equation we use, okay, because we have the entropy here. We also know for the ideal gas, the du is the cv dt equals to tds minus pdv, okay? And then from this equation, we will have is the ds equals to cv dt plus pdv, okay? And then the delta s, we can do the integration. Okay, this is what we get. This is how we calculate the change of the entropy of the ideal gas. But the question is, in the reality, I mean, we're not only deal with the ideal gas, okay? We not only deal with the ideal gas, because through the ideal gas, we can, by using the ideal gas, we can change this term, the P equals to what? Oh, I'm sorry, so this is 1, so T, okay? For the ideal gas, P divided by T term actually equals to what? Equals to NKV, right? We directly put this relationship to this equation and to the calculation, correct? But this relationship doesn't work for the real gas, correct? And then the question is, how can we calculate the entropy change of the real gas, okay? Can somebody of you go to the restroom to grab some paper towel? The classroom become more and more ridiculous. There's no provide marker, and right now even disappear, the user disappear. And I guarantee that next time the whiteboard disappears. They force us to use the screen. And then at the end of the semester, electricity goes up. Oh, that probably happened during the hurricane. Just give me some time. I hope that the dean and the president can see my class footage and hear my complaint. There's no marker pen, there's no eraser in this classroom.
Preeminence, supposed to be all sorts of stuff coming in.
What's that?
They announced to reach preeminence, supposed to be all sorts of stuff coming in, right?
Yeah.
Surrounding and permanent markers, or exo markers.
Yeah, they should get some, but not permanent marker.
Not
Where's that guy? Oh, there's no even tissue in the restroom. Oh, here we go. At least we still have tissue in the restroom. Thank you so much. Okay, I'm sorry you missed so much information already. It matters. Oh, it matters. You cannot pass the midterm. Oh my God. That's ridiculous. And then the question is, how can we calculate of the real gas, okay? Or the PV system, okay? How can we calculate the entropy change of the PV system? Basically, that means the volume pressure change, okay? We don't consider other factors, magnetic orders. No, we don't consider that one. We only consider the PV system volume change, pressure change, okay? But for the regular PV system, we simply do not have this relationship. We simply do not have this relationship, okay? This is only for the ideal gas. But what if we don't have this relationship? How can we calculate the entropy, okay? So that's the question. Okay, so in order to solve this equation, to solve this problem, we need to know, we start from beginning, okay? So, so the S is a function of T and V, okay? We just assume S is a function of T and V, okay? I will tell you how can we change that later, okay? We just use T and V as independent variable now, okay? Temporarily, because we can change P. We can change PV to P. We can use PV, we can use TP, doesn't matter, okay? Let's start with the TV, okay? So, then the ds will equals to partial s, partial t, v dt, plus partial s, partial v, t, dv. Okay, so this is the just mathematics, okay? All right, so then in order to calculate the change of entropy, we need to know, we need to have information of each of the term here, correct? Okay, let's see the first term, okay? Partial s, partial t, v. What that mean? That means if a system, this term indicate the entropy change as a temperature, as a function of temperature, but under a constant volume. Correct, everybody? So can anybody tell what this term means? Huh? What this equals to? Can anybody tell me?
PV is 0.
Huh?
PV is 0.
What?
PDV is 0.
PDV, yeah, PDV equals to 0, exactly. So, yes, you're right. That means du equals to TDS, and then minus PDV, okay? Remember, it's the PV system, okay? And this term equals 0. Correct, everybody? And then, what the du equals to? Because we do not change the volume, then the change of dV only equals to CV dt. Correct, everybody? Okay, remember one thing is, du equals to CV dt, this one always works for the ideal gas. But for the actual gas, it's not always in this kind of way. You know what I'm saying? I mean, this equation not always work for the real gas. But if the volume doesn't change, we have this equation, okay? That means, in other words, partial U, partial T, with the constant volume, we have this definition. You know what I'm saying? But for the ideal gas, yes, we have this relationship. Okay, this is only for the ideal gas. But for the real gas, we have this relationship. Okay? But in any kind of sense, but it doesn't matter because we only consider the constant volume process. Okay? For the constant volume process, we have du equal to CVT, correct? And then this part equals to TDS. Okay? And then what we have is partial S, partial T as a constant volume equals to CV divided by T. Correct, everybody? And then this one equals to CV divided by T. That's fine. Okay? Okay? This one equals to CV divided by T. What about this term? If the temperature is constant, we need to calculate the change of the entropy as a function of the volume change, right? How can we know that? This part. So there's no way for us to directly calculate, okay? Basically, I mean, you can, in other words, you can measure the change of the entropy as a function of temperature by measure the heat capacitance of the system. Heat capacitance is measurable, right? But for that one, how can we change this expression to some other measurable parameters? Okay? So in order to answer your question, we need to go through, typically we go through the Maxwell relationship. You can see that one. Partial S, partial V as function of T, with a constant T equals to partial P, partial T as a function of V. So the importance of the Maxwell equation is we change the partial derivative relative to the, relevant to the entropy to some other thermodynamic parameters, to other measurable thermal parameters. You know what I'm saying? So basically, we do not have direct measurement on entropy. We have the definition. We can calculate, but we do not measure it directly, right? But we can change this relationship to some other measurable parameter. P is measurable, temperature measurable, but the volume, of course, is measurable, right? So in that sense, we can change this equation to dt plus partial T, partial T. Okay? And then if you want to calculate the delta S basically is equals to CV. And the one thing you need to be very careful is that for the real gas, or the actual PV system, the constant pressure, constant volume thermal heat capacity can be a function of temperature. It may not be a constant. Okay. For the ideal gas, we know that this one equals to what? What's the value of it?
3
Right? This is only for the ideal gas. But for actual system, the CV is a function of the temperature. Okay? It's a function of temperature. Okay? This is only for ideal gas. But the more general case, CV equals to partial U, partial T. Okay? This is the general definition. Okay? So in that case, it's a function of T. Okay? So we need to make sure that the label is that it's a function of T. This is something, in other words, by using the Maxwell equation, we can transform the unmeasurable parameter, we can express the unmeasurable parameter with some measurable parameters and then do the calculation. Okay? I hope this explanation can help you to understand why we need to introduce that equation. Okay? But of course, what we can do is just here, okay? If you want to continue the calculation, we need to know how the pressure changes as function of temperature. Okay? But again, if we go back to move back to the ideal gas, we know that partial T, partial P, partial V at a constant with a constant volume equals to what? We can calculate, okay? For the ideal gas, we know that P equals to NKT divided by V, right? Then partial P, partial T equals to NK divided by V. So we just go back to the original expression. Other point? Is that clear? Simple?
I have a quick question.
Yeah.
Could you explain again how to get CV by T for the partial S, partial T term?
Okay. So his question is, how can we change the partial S, partial T as constant V to the part CV divided by T, okay? So for that one, we just go back to the original equation, okay? So this is the du equals to PdS minus PdV.
And we don't have PV.
We don't have this term, right? And then you can think of it that way. Is that then if we don't have PDV, then the du is just equals to delta Q, right? And then delta Q with a constant volume equals to CV dt, correct? And then you have the TdS equal to CV dt, okay? And then you will have the partial S, partial T with a constant volume equals to CV divided by V. Is that simple? So if I give this one in your final examination, can you finish that? In your midterm, can you get the correct answer and pass the final examination? I mean the midterm. Oh, by the way, let me ask a question. So when is your qualify?
17th.
Everybody? How is it possible?
What was the question?
When is your qualify examination? You don't have to qualify, don't worry. What about your undergraduate student? Are you undergraduate or graduate?
Yeah, undergraduate. No.
Yeah, you two of you don't worry too much about it. Don't worry, I definitely give you both of pass real fast. we want to encourage any graduate student, but we want to give the graduate student a hard time. Okay?
You're scaring us away right now.
Huh?
You're scaring us away right now.
Nah, I'm not scared of you guys, okay? So graduate student means you're going to suffer more, and we're going to push you, challenge you, make it hard, make your life miserable. Everybody catch what I'm saying, right? But the good thing about two of you guys, if you join UCF as a graduate student in the future, you're going to take the same class. You know what I'm doing. Probably even do not need to take the same class. We directly give you the pass. Okay, anyway, question. What about if I choose T and P as an independent variable and calculate the delta S? Okay, I give you 5 minutes to solve this problem. A hint, okay? Give you a hint. ds equals to partial s, partial t, as constant p, dt plus partial s, partial p, partial t, constant t, dt. Once again, this is not necessarily a gas. Any kind of PV system, solid, liquid. As long as we can use P and V to describe the state of system, we can always use this kind of equation. Not necessarily to be ideal gas.
Operations and this is still true.
What do you mean not blue?
The numerator and denominator.
Yes. And I find actually each of these marker only survive for 2 classes.
You have 3 more.
Oh, I have 12 more in my office. And I also got the cartridge for that. Yeah, I mean generate a lot of this kind of the plastic trash. Well, every 2 classes we need to get rid of one of them. It's incredible. That's the reason they want us to go to the paper list. Well, the other way, probably just go back to the blackboard and the chalk. So what topic is going to have on your qualified examination?
Sugar-based diagram.
This diagram?
He already cleared
He
it.
knows everything.
He already cleared it, so
Was it?
he already cleared the qualification exam.
But you told me it's next month, right?
No, he is in second year, so.
Oh, you are in second year?
Yeah,
Yes,
he's
ma'am.
in second.
But I think for the qualified, you have some question about thermodynamics, right? But you haven't taken the class. How do you answer the question?
I did not. It's a pre-qualifier. It's a pre-qualifier, so like only 2 out of 10 people pass, and then everybody else take the actual qualifier at the end.
Oh, I see. They asked me for some question about thermodynamics, then I can give you really hard questions. Let me think. What are the questions?
Should we
really hard?
forget 12 marks
Just ask a
already?
homework question.
No. That's so that's so easy for you guys. Let me think. Let me ask you right now to see how many of you can give me an answer.
Yeah. It's not theoretical based, right, Professor?
It's not theoretical based. It's just, you don't need to write equation, just some qualitative questions. I'm thinking what kind of the question can answer. Okay, so probably can answer some question like this. So finish this job first. And then I'm sitting here, try to avoid the camera. So just in case, so somebody see my class, they will not see that. Okay, I'm just sitting here lazily and. So give the MI students some good experience. There's nothing to complain. We have no evidence.
Professor, is it possible to not record the class?
No, you cannot. Everything record automatically. So we have no privacy in this room, okay? But you can choose where the camera goes to record. Right now, it's only record what's happened on this whiteboard. I have a monitor there to show what he's recording.
Where do you find the recordings? Where are the recordings?
Go to the canvas. You know that go to the myucf.edu and then go to the web course at UCF. And on that page, you can have the link called Canvas or something, right?
Yes.
The one you submit the homework, whatever. And on the corner, there's a link called the Panacto or something.
Oh, okay.
Yeah, and then you can find all this kind of video footage. I never see that myself because it looks really weird. You know that you're looking at yourself. I mean, everything becomes really awkward. It makes me feel very embarrassing. Okay. Oh my goodness, why I'm looking like this? Okay. I think that if some supervisor, if some professor got kill himself just because you look at the video. Oh my goodness, I never expect it looks like that. Okay. Anyway, let's come back. I'll come back. Okay. What do we need to do? Just follow what we just had. Okay. We need to calculate the both terms. The same thing. Okay. For the p, right now we are in the constant p, right? So, but for the constant p, I mean, for the constant v, we use that one, right? To do the calculation, correct? Remember? This is for the constant v. Because the reason is, for constant v process, this term automatically disappears, right? What about for constant p? We use the entropy, right? dH equals to TdS plus VdP. Correct, everybody? And then this term disappeared, right? This term disappeared, correct? And if this term disappeared, I mean, the other thing is, if this term disappeared, then this one is what? What do we need to calculate? Is what? Then what is the DH? What's the expression of DH? DH is the what? CP dt for the constant pressure process. Correct, everybody? And then we have and then this one equals to TdS. And then partial S, partial T, as a constant pressure equals to Cp divided by P. Correct? Okay, right now we know that term. Cp divided by P. Second term. If you don't know, look something here. I mean, he asked me a question whether we can flip this kind of fraction. Okay, we can put the partial S, partial P. That's fine. But if we use that one, partial S, partial T, a constant V, it doesn't work. Let me see where is that one. Partial S. Okay, here we go. We find this relation. Okay, partial S, partial P as constant T equals to partial V, partial T as constant T. Right, and then this one becomes negative partial V. Partial T. P. Okay? Same thing again. So we change something, some unmeasurable parameters to some experimentally measurable parameters to do the calculation. Correct, everybody? Simple? If I put this one in the midterm, you can find you can finish it up, right? Probably during your qualifying examination, before the professor asks you a question, you can ask them first. Okay, let me ask you a thermodynamic question first to check whether you are qualified for the qualifying examination. I think I'm going to be fired by the department. Okay.
But do we have the right to ask? No. Do we have the right to ask?
No, you don't have the right to ask. It depends. It really depends. Depends on the university system, depends on the individual who gives the class, okay? Let me share you a funny story when I go back to the PhD. When I was the graduate student. One day, I was working in the lab, holding some chemicals. And then there's a very senior professor wandering around the hallway. He's always like that, okay? When he's thinking, just in the hallway and doing something like this, going back and forth. He's a troublemaker. How about I let you know why? I open the door, hold the chemicals in my hand. I did not see it. The door is totally, there's no window on it. And he was just outside. And when I opened the door, he said, oh, it just scared me. I mean, oh, I'm sorry, professor, but I really apologize. But one thing, you know that if the door is open inside into the hallway, we always have that construction. You know that one thing? The door always have some, always put inside inward to prevent the door to go into the hallway. You know what I'm saying? So that in case, in principle, the door should hit you, even I open it suddenly. The other thing, this is research lab. Do not stand somewhere in the corner. Otherwise, problem got this is what I told him. And you know what he said to me? Hey boy, you know that I'm a senior professor, but you're just a student. You cannot talk with me in this way. I told him, yeah, I understand. I'm sorry if I make you feel, disrespectful, but honestly speaking, everybody should follow the same safety safety guidance, okay? And he got really angry and reported me to the vice president. And then the department started to investigate the case. And then I told him the whole story. And you know what the consequence? The university asked him to, okay, take some safety training. That's a reasonable university, right?
So the professor.
Yeah, the professor needs to take some safety training.
No. If I ask about the thermodynamics, you have to learn thermodynamics, right?
You can try, let me know the outcome.
I don't want to include.
I have so many bad ideas. Okay. Okay, let me tell. Yeah, there's a story have some continuity. And then during the semester, I was in Houston, Houston, Texas, to have my PhD. And then, the similar to Florida, right? They have hurricane all the time. And during one time, in the building, everybody office are fine. Everybody's office, the office of everybody's fine, except that guy. Have the flood. The leak from the ceiling. That's the only leaking spot, and all the water from that storm comes to his office. That guy has a really beautiful Turkish blanket on the floor, made of wool, you know what I'm saying? Completely destroyed. And I celebrate. Anyway, so that's my dark history, okay? Anyway, so we have two expressions of the entropy. Correct, everybody? So both are correct. So you can select them according to your personal preference or like convenience. For example, if you want to calculate the change of entropy under a constant temperature, but the variable V, you prefer to choose this one. Correct, everybody? Right? If we only consider the change of the volume, then we can use this function, right? Because this term disappears. If you want to only calculate the entropy change as a function of P, you can use this equation. Correct, everybody? Is that true? But the question is, what about if we want to calculate, if the system only has the temperature change? Okay. What about the temperature change? Which one should I choose? Basically, for the isothermal process, which one should I choose? For the isothermal process, which one should I choose?
Second one.
You know that for the isothermal process, the temperature doesn't change, right? But only the pressure and P both change. Which one? What's up?
I just have a different question. Is the CV over T supposed to be CP over T? Or did that change between those two?
Which one?
The first line ds equals CP over T, is that supposed to be CP over T?
CV or T? Let me check. CV over T. CV over T part of T part of T. I think it's right. It's a CV over T. The second one is a CP over T. But the variable is different. This one is dV, this one is dP.
Okay, and then also, are the CVs and the CPs going to be functions of temperature as well?
Yeah.
Okay.
Yeah, exactly. Okay, I mean, let me repeat the question. So if the system have the constant, pressure, have the constant volume, if the system has a I think I just said something wrong. If the system has constant volume, we prefer to use this equation to calculate the the entropy change, right? Because if you have constant volume, this term disappears, right? We only do the integration of this one. If the system has a constant pressure for the calculation of the entropy, we can ignore this term and only calculate this one, right? But what about the isothermal process? Which one should we choose? For the isothermal process, which expression should we choose?
Then we have to derive another equation. We have to use other equation.
No, there's no other equation. There is other equation, but
No one is free.
yeah, there's other equation, but they are more complicated. The answer is I can use either of them, give you the same result. Okay, let me try. Okay, for example, if I use the first one, for the isothermal process, because this one is the first equation, this one is the second equation, you will see that they give you the same result. For the first one, we know that the delta S will simply equals to integration CV P dt. Okay? Do it. Equals to partial P, partial T, V dV. Okay? And then for the from the equation 2, what we have is delta S equals to minus partial V, partial T, divided by P. Okay, and these two expressions give you the same result. Okay, you can try by using the ideal gas to have a test to see whether they give you the same result. Okay. For example, if I put the ideal gas equation into it, we know that the partial P, partial T, as constant V, this one equals to what? Equals to NK divided by V, correct? Is that right? For the ideal gas. Yeah, correct? And then we put this one in. Let's put it for ideal gas. Okay, and then this one becomes integration of NK V dV. And then this one becomes NK ln V final divided by V initial. Right? The same thing here. So if we use this equation, partial V, partial T, P equals to what? Equals to NK divided by P. Right? We can also put this one in, and this one becomes minus integration NK divided by P dP equals to minus NK ln P final divided by P initial. Right? Correct, everybody? But we know that the ln P final divided by P initial equals to ln NK T divided by V final and NKT divided by V initial. Okay, because we already mentioned this is isothermal process, then this one simply equals to VI, VF equals to minus ln VI, V initial. Okay, you can see these two equations give you the same result. Correct, everybody? But I only use the ideal gas as the example, but for the more general case, they should give you the same result, okay? Questions? Comments?
So we can use both for.
You can use the either of them. Okay. Okay, so which one? I think you asked me your question, right? Right now we use the TVPP. Okay, that's supposed to make your job more complicated. What about S as a function of PV? Do the calculation. So still the same thing. I mean, yeah, we'll do the calculation. We want to calculate the change of entropy. We follow the same thing, okay? Partial S, partial P, V, dV, plus partial S, partial V, P dP, okay? Again, the same issue. We cannot measure the change of the entropy as a function of P measured directly. The same thing here, we cannot measure the change of entropy as a function of V directly. So we need to change these two terms to some measurable thermodynamic parameters, okay? So the you can use the heat capacitance to do the job. You can use something here to do the job, okay? Oh, by the way, so we can add, this 4 is Maxwell equation. Another two important and useful relationship on this, okay? Partial T. Okay. So basically, this question I'm asking you to calculate the partial S, partial P as a constant V. See here, this one is a partial S, partial P as constant P, partial S, partial V as constant T, partial S, partial P constant T. Right now, we're asking partial S, partial P as a constant V, and partial S, partial V as a constant P. Okay, so it's not T anymore. We need to calculate these two terms. Let me ask you this question during your pre-qualified examination. Now let me give you some background. Okay, we can use laser to cool down the atoms. This is because the entropy of the laser beam is very low. So we use the low entropy atom objective emission laser to remove the entropy from the atomic system and cool it down. That's the background. The question is, what type of laser prefer use? Okay, we have a laser looks like this. The bandwidth, for example, the bandwidth of the laser is 10 gigahertz. And the other laser beam, the bandwidth is the 10 megahertz. Which one can help us to reach a lower temperature? Use the thermodynamics analysis. I'm just kidding. I don't think you can answer it. Forget about it. Let me think more realistic. For example, I have a box of match, and then suddenly drop it down on the floor, and the match have random distribution, different orientation. Calculate the entropy of it. Huh? Oh, you got an eraser?
Yeah.
Where it is?
It was just on the ledge behind me.
Oh, all right. Thank you so much. Do you know who is going to give you the pre-qualify in October? Who is the person going to give you the test? Nobody knows?
either Dr. Fang or Dr. Leon.
Dr. Fang is the associate chair, right? And the other, who is the other?
I think her name is.
Oh, I know her.
Lorraine.
We're in the same building. Dr. Fang is teaching you the structures of material, something else. Have you got the answer for that question?
Is that the first half, partial S, partial P, is it VDV or VDP?
VD, what region? Oh. Yeah, it's VDP. Okay, so in order to answer that question, first of all, we need to know another relationship, okay? So we know the partial P, we know the partial S, we know this relationship, right? We know the partial S, partial T, V. We know this one, right? Is here, correct there? Correct, everybody? So the question is that whether we can transform the partial S, partial P to something include partial S, partial P. The conclusion is partial S, partial P, V equals to partial S, partial T, V, and the partial T, partial P. Okay, that's the conclusion. So basically we can replace that one. And for this one, the same thing. The partial S, partial V, and partial S, partial T. Okay. First of all, let me explain the physical reason for that. Okay. The reason is right now we are calculating under the same, for example, this term. What we are calculating is under a given fixed volume, how the entropy change following the change of the pressure. Correct, everybody? So at the constant volume, we know that the change of the pressure is going to change the temperature, right? And the temperature change is going to change the entropy. Basically, we are looking for this relationship, but we can expand the chain, right? We know this one, they are linked to each other, but we can also link them through a T, right? We can add a T there. So basically, we are not directly calculating the effect of P on S. We calculate the effect of P on T first and calculate P on S. Right? By doing that, we know this from, right, from the Maxwell relationship. We know the partial S, partial S, no. Partial S, right, but this one is just CV divided by T. Correct, everybody? And this one is what? Is just CV divided by T. Okay? So we know that. But this is just the argument. So we're going to prove it mathematically. Okay? Mathematical proving, something like this. Right now we're defining P and V. Correct, everybody? But what do we know? What we know is what we already know is the S as a function of V. This is what we already derived, right? We know all the information here. So in order to get this expression, actually we can write the T as a function of PV. Correct, everybody? So then these two are equivalent. Correct, everybody? We know this expression, right? We already solved this problem. S as a function of T and V, right? But what we want to know is as a function of P and T, and P and V. So we can further expand the T as a function of P and V. So eventually, and then these two expressions are the same. Correct, everybody? In other words, we use the t as an intermediate variable, right? And then we can do the derivative on this equation, right? Then the ds equals to partial s, partial t, v dv plus partial s, partial v t dt. Right? And for the dt, we can continue the derivative, right? It's partial s, partial t, v, dv, plus partial s, partial v, t, times partial t, partial p, v dp, plus partial t, partial v. Correct? And then this one equals to partial s, partial t, dv, together. What I'm doing? I think I'm doing something wrong.
You reverse the dt and dv on the first one.
Wherever it is. What a mistake I made. And the next question you should ask me, why do you are qualified to teach the thermodynamics? Which term is wrong?
The dv and dt should be
Which one? Give me a second, I'm going to figure it out. Which one?
like you have ds over dt times dv, so that's not in the unit defense.
Ugh. Yeah, then it's totally wrong. Yeah, my brain's not working. Yeah, but anyway, let's repeat what we do. Okay, so then this one is a partial s, partial t, v. We can further expand the dt, right? Then it's partial t, partial v, p, dv, plus partial t, partial p. You know that the university cannot fire me anymore. Because I already showed them I have some mental disability. They cannot fire me. And my brain stopped working, so it's not my fault. It's just my brain doesn't work. You cannot fire me. Anyway.
You can't say that, you just won an award, didn't you?
So what?
Did you just win that career award? Did you just win that career award?
Oh, forget about it. I don't know what they're talking about.
Yeah, no, I did.
I really, honestly speaking, I don't want people to talk about this career work. I mean, yeah, because they keep saying that again and again. I mean, yeah, but.
Yeah, you got some grant money.
But the thing is, if something happened 1 or 2 years ago and we keep repeating, talking about the same thing, that means I did not make another achievement in the next few years. You know what I'm saying? It's just like that. I'm still telling like that. You know that when I was 10 years old, I won the national award. Yeah, but right now you're all 40 years old. Oh, I'm sorry, I just disclosed my age. Okay, anyway. So, yeah, that's it. I checked the MRI of my brain. There's some smooth stuff happening inside. I don't know what's going on. Hopefully it's not tumor or whatever. But honestly speaking, I feel headache even right now. But anyway, so right now we can see the partial S, partial P gives this result, okay? The partial S, partial P. That's what we have. But you simply do not need to use this kind of very long expression to replace this term, okay? Follow the same thing. This term still equals to partial S, partial T, the P, and partial T, partial B. Okay. And actually, you can prove this expression and this expression are the same, okay? But you can use either of them. But I prefer that one. This is simpler. Okay? So basically, mathematically speaking, for any kind of function, partial x, partial y is always equal to partial f, partial z, y, partial z, partial x, y. Okay? Yeah, this is just like the conclusion mathematically. So you can always insert the t here and make use of the relationship you already know. Any questions? But we don't replace the this variable. Okay? We always keep that the same. We cannot change this one. We cannot change that one. Okay, but what if we indeed need to change the y here? So we're going to tell you another. Anyway, so I'll give you some seconds. So any questions here on this expression? No? Let us do a practice. Let us do one more practice. Okay? Okay, we already did 3 practices on the entropy. I think you're about exhausted. Okay, I think you got the really hate entropy right now. Okay, at least fine. It's practice always a painful process. Okay. Don't worry if you cannot understand, if you cannot follow very closely to what I'm saying, because I was also struggling when I prepared for the class. I mean, I lose most of my hair during preparing the class. But I do not lose them, but they turn white. We know that the u, typically we use the u as a function of t and no, a function of s and v, right? Because we write the du in terms of t ds minus p dv. Okay. Now, what if I choose the what about if we choose t and v as independent variables? Then calculate the du. Okay, find the expression of du. Of course, the partial u, partial t, v, dt. Okay, so your job is to calculate these 2 terms. There's a bad joke. I have no idea whether I want to keep talking about that one because everything seems boring. Probably got fired. Do you know what's a PhD mean? What's a PhD mean? Let me write down on this board, okay?
Oh, because they can't see on that one?
That's what I'm suffering. Okay, nothing got recorded. Anything else, anything? Yeah, you can find quite a lot of weird person, especially professors. In the building, there's one professor. We're in the same department. But whenever I see him, you never say, never greet him, never say hello, never say anything, just look at him. What's going on with this guy? We know each other. And he also came to my office asking for some document. But whenever I see him in home, just as a stranger, act as a stranger. University, very interesting place. We have the interesting guy.
No, it's pretty much same, even in the class.
What's that?
It's pretty much same, like even for students. Yeah.
Oh, really? I don't know. I don't student. Dynamic professor. Very weird. And one thing I'm worrying about is that I'm gradually become this kind of weird professor. Boring and very self-centered, and do not have open mind to a new stuff. You know that I force myself to admit that AI is there. We want to make good use of it instead of reject it. It's a trend. You know what I'm saying? So we're going to discuss in the faculty meeting tomorrow about how can we include or exclude AI in the class. But for my opinion, it's a trend that there's no way for us to deny it. But, yeah. The question is that how can we make good use of it?
Why do you hate AI so much?
What's that?
Why do you hate AI so much?
The reason is I don't hate AI, but the most important thing is if you guys relying too much on AI to do the homework or midterm, we cannot ensure the teaching quality anymore. Because everybody will have the good result, but that means that you really know what you're talking about. So that's something we're worrying about. We are not worrying that you use your AI for your research, but we want to make sure that all the students indeed understand what we're talking about. You know what I'm saying? That's to ensure the teaching quality, right? For the university, we're not teaching you how to use AI, we are teaching you the knowledge, right? The other thing is, we want our students cannot be easily replaced in the future job market. You know what I'm saying? You have to be competitive. You know you have the innovations. You know the new techniques instead of just typing command into the AI. So that's something we're trying our best to solve. Okay. But
there's certain things that AI can do even better than humans than how they're supposed to.
there is. I mean, just like it's not like not necessarily to be AI. The computer can do a lot of things better than a human being, right? Okay, calculate this one. Can you do that? You cannot, right? What I can do is only calculate this one. The computer can do much better job than me, right?
Oh, is the eraser not cutting it?
Huh?
You don't like the eraser? You're just using both.
Oh, I just forgot where I put it.
So maybe it disappeared in the first place because you lost it.
Yeah, probably. That's the reason I told you I have something. Anyway, let's come to this one. Do not listen to the joke. I'm asking you to relax and finish your job. Okay? Do not just focus on what I'm talking about. I mean, you need to go back. The same thing, we need to calculate this term. Okay. So what do we know? What do we know from this equation? We know that we know the partial u, partial s, right, and v, and we also know the partial u, partial v as a constant s. Is the what? This one equals to v, right? That's what we know. But we need to solve something like something here. So first, term by term, okay? But for that one, you already know, right? Partial u, partial t, constant v. This is what? Just cv, right? but we need to calculate this term, okay? Let's see how can we do the job. We can insert, let me see how can we do the job. Okay, so we're doing it that way. So we know the u as a function of s and v, okay? And in order to express with the variable of t and v, we can put it that way. U equals to s p v, correct? And then the du will equals to partial u. We know that we can make this job easier. T ds minus p dv, right? And we put the s as a function of t and v. So this one is a t times partial s partial t v dv plus partial s partial v t p dv. Okay. And then this one equals to t partial s partial t as function t v. What's that? What is this? What is this? Partial s partial t as constant v.
CPU.
Yeah, that's a CPU. It's fine. I mean, we don't need to worry too much about this one. Let me see whether we need to care about this term. Is that something wrong? Oh, yeah, something wrong again. The same mistake. It's weird. We don't need to calculate this term. Anyway, so we don't need to worry too much about this term. So what do we need to, since we need to calculate the partial u, partial v, we only need to consider this term and this term, correct? And then this one equals to t. We don't worry too much about this term. But to talk about this one. T times partial s, partial v, t minus p. Okay? And this term basically gives you the partial u, partial v. That's the concept. Correct? And then this one equals to what? Equals to partial s, partial v, minus p. Correct? And again, the partial s, partial v as function of t, you can read it from here, right? So then this one essentially equals to cv dt plus t dot partial p, partial t, v minus p. That's it. And then everything can be calculated, and everything can be measured, right? Okay, so we have a practice class this time. So basically, the purpose for this class is just tell you that how can we exchange the independent variables. Okay, we have different ways to do the job, but sometimes you cannot find the relation, especially when the variables or the functions involve entropy, because we cannot directly measure them. Then use the Maxwell equation to replace the term include entropy. Okay, so you can express entropy term with some measurable parameters. And that's the use of Maxwell relationship. Okay, I think that's pretty much for the class for today. And next time we're going to briefly introduce the concept of the chemical potential and move on to the next chapter. We're going to use of the knowledge we learned so far to analyze some practical problems, phase transition, forming of Lloyd, the phase separation from that. So basically, the text for basically we already finished the introduction of all the fundamental knowledge for the thermodynamics.
I have a question.
Yeah, go ahead.
I think this is,
What?
branch should be here. And,
I told you I have some, I have some little issue.
and why is this term usually not?
Because this is the question you. du equals something t and something dv. So this one is partial u, partial v. Partial u, partial v.
So this is from here, like this term is from here, and this is what we wanted over here. Oh, so that's how we relate. And how are these two equivalent?
From the Maxwell relationship.
Oh,
right?
okay. Thank you.
Wherever is still here. I find I'm not very myself today.
Is this okay for like the homework or just writing out my
As long as you don't have ChatGPT or Gemini marker on it, I'm okay.
Should be good.
You know, one of my students give one, I asked my student process one image for me. I know I'm done. I write the code for it. And then there's still this kind of logo on the corner. I'm old, but not that true.
Oh, it's Gemini, right?
It's Gemini. And the other thing is that you know that I try to use Gemini to solve some mathematical problems. And I have a free edition, and you only can ask 2 questions. I type in. The question is very complicated. The question is like this. Show me the fidelity for the quantum entanglement of 2 photons. I have the entanglement in such a form. Oh, it's giving me a really beautiful answer. And then when I'm asking the next question, he told me, okay, you already reached the limit. Then I just pay $20. And then all the answers disappear. I need to re-ask them. Okay, the same question, show me the fidelity measurement of the 2 photon entanglement in this form. It just gives me some random answer. I mean, you just,
It's changed. It changes.
yeah, exactly. I pay it, but it doesn't work anymore.
That's why I'm not paying for the subscription or anything.
And next time I can show something. Very fun. I have some experimental image. And since the student already used Gemini to process, I tried myself. And the result looks really good. I mean, it's something like the multi-crystal structure in diamond. Okay, the multi-crystal structure is looked like this. You have quite a lot of crystal domain, something like this. You have some domains, different angle, and ask to make the image have a high resolution. Successfully done. I put the same figure in ChatGPT to look what it looks like. You know what's the final result? The final result looks like this. It's giving me a flower.
Make your life very good, right?
That's beautiful.